Dear students, in this video we are going to discuss about energy. The capacity of doing work of an agent is known as energy, and it is a scalar quantity. The unit of energy is joule. Let's say you want to move a block. So if you want to move a block, what you will do, you will apply some force on the block and this block will move by a distance. Correct? Now what you are doing some work on the block. What you will feel after some time, you will feel tired. Why? Because you have expended energy in doing this work. So basically, your capacity of doing work is related to your energy. So the capacity of doing work of an agent is called energy. Okay, now let's look at the types of energy. There are a lot of types of energy. One of them is nuclear energy. Then there is kinetic energy. See, this stone which is held in the hands of this person, when let go, will fall down and it will gain some energy. How it is gaining that energy? Because initially in this configuration, he has some energy known as the potential energy. Okay, now there is electrical potential energy or electrical energy. See, these two charges are separated by a distance. These two charges, when let go, will move towards each other, gaining kinetic energy. So basically, in this configuration, they have electrical energy, which can be converted to kinetic energy or any other form of energy when they are let go. Now there is light energy, which is the energy radiated in form of light by this electric bulb or the sun. Okay. Now let's talk about kinetic energy. Kinetic energy is energy associated with the state of motion of an object. Look at this truck. When this truck is moving, it will have some kinetic energy because it is moving. When this truck is at rest, that time its kinetic energy will be zero. So basically, the kinetic energy is the energy which is associated with the state of motion. The faster an object moves, the greater is its kinetic energy. And if an object is not moving, say the object is at rest, then the kinetic energy is zero. The formula for kinetic energy is half mv square. And there's one more thing. We can relate kinetic energy and momentum by using this formula, which says kinetic energy is momentum square, that is p square by 2m. This formula is very simple to write. You can say that p is momentum, which is mv, so it is mv square, correct, divided by 2m. So you'll have k is equal to, if you see this, it is m square v square by 2m, correct. So if we simplify this, what we'll get half mv square, right. So this is the formula for kinetic energy. So remember this formula, which is very important. Work done on an object changes the kinetic energy of the object, and the formula relating to this is that the total work done on an object is equal to change in its kinetic energy. Now let's move on to the next slide. The potential energy is the energy possessed by a body because of its position, its shape, or its size. Let's say you have an object which is placed at a height from the ground. Okay, now in this configuration, you know that this object is going to have some energy, because when you let go of this object, it will start to fall down and it will gain some velocity. Now, if I have an object which is kept at a higher height, more high, the energy of this object will be more, right? So this energy, the potential energy of this stone, is related to its position. Similarly, let's say you have these two charges. There are two charges. What happens when you let go of these two charges? When you let go of these two charges, if the force is attractive, then the charges will start to move towards each other. If the charges are moving towards each other, they will gain kinetic energy. The kinetic energy that they are gaining is because of the initial potential energy that they had. So, because of this configuration also, these charges have some potential energy. Now, let's look at this spring. What happens when you compress the spring? When you change the shape of the spring, because of that changed shape or the deformation, the spring will store some energy, and that energy is also potential energy. Now we divide potential energy in two different categories. One is gravitational potential energy and the other one is elastic potential energy. Gravitational potential energy is the energy stored in an object because of its height. So let's say if an object is at a height h from the reference. Okay, so what we are doing, let's say ground is my reference point and this is my ground. Okay, so if some object is at a height h from the ground, then the potential energy stored because of this configuration is equal to mgh. Okay, now there is something known as elastic potential energy. Elastic potential energy is energy stored due to deformation or the configuration. Okay, so see here, because I have two charges, there is some potential energy stored in these two charges, and if I compress this spring or even if I extend this spring, in both the cases, the spring is getting deformed, and because of that deformed shape, the spring will have some potential energy. And because of that deformed shape, the spring has stored some potential energy. That energy is known as elastic potential energy. In the next slide, we are going to discuss about law of conservation of energy. Law of conservation of energy states that energy can neither be created nor be destroyed, but it can be converted from one form to the other form. If you look at this stone, what happens when you let go of this stone? Let's say this is the ground and you let go of this stone. The stone will fall down, correct? The potential energy of this stone is decreasing, but as it falls down, it speeds up, so the speed of the stone is increasing as it is falling down. When speed is increasing, that means the kinetic energy of this stone will start to increase. So basically what you see, the kinetic energy is increasing and the potential energy is decreasing. What is happening is the potential energy is being converted to the kinetic energy, but the total energy of the system will remain conserved. Similarly, in case of pendulum, which is moving like this, at this point, the pendulum is at a higher height, at a higher point, so it has more potential energy. At this point, the pendulum is at a lower point, it has less potential energy, but at this point, the pendulum has zero kinetic energy because it stopped moving at this point. At this point, the pendulum is moving and it will have some kinetic energy. So basically what is happening in this pendulum, the kinetic energy and the potential energies are getting interchanged with each other, but the total sum of the energy is conserved. In the next slide, I am going to discuss about conservation of mechanical energy. Conservation of mechanical energy basically means if there is no air drag or frictional force acting on the object and there is no external force that is acting on the system, okay, then the sum of kinetic energy and the potential energy remains conserved. So if you look at this, this is ground and this is an object. Now first we have to consider the system. The system is this object and the ground itself. So basically our system consists of earth plus this object. These two makes our system. Okay, so let's think about this. For earth and the ball, there is no external force that is acting on them, correct? Now, what happens is when you let go of this object from point A, when it falls a distance x, the potential energy is decreasing, but the kinetic energy is increasing. According to conservation of mechanical energy, let's say the speed at this point, the speed at B is equal to in this direction and it is equal to VB, right? So according to conservation of mechanical energy, I can say that the total mechanical energy at A is equal to total mechanical energy at B is equal to total mechanical energy at C. So basically what I can say that the sum of kinetic and potential energy at A, which is, let's say at A, if the object has velocity equal to 0, so the kinetic energy is half m 0 square plus the potential energy, which is equal to mgh, is equal to mechanical energy at point B, which is half m Vb square, which is the kinetic energy at point B, plus the potential energy at point B, which is mg, and the height right now is h minus x, correct? And this is also equal to the mechanical energy at point C. At point C, if that the height is 0, so the kinetic energy is going to be half m Vc square plus mg into height, which is 0. So basically according to conservation of mechanical energy, I can say that mechanical energy at A is equal to mechanical energy at B is equal to mechanical energy at C. Okay students, in this slide we'll see the conservation of energy for a pendulum. See, The pendulum has maximum potential energy at these points, these extremes, and maximum kinetic energy at this point. Okay, the point A. See, at these points B and C, the pendulum will stop moving, and at point A, it is at the lowest point. So if I want to apply conservation of mechanical energy, I can do that very simply. At point A, the mechanical energy is equal to the mechanical energy at point C. Okay, so at point A, the mechanical energy is half m va square. Correct? Va is the speed of this object at point A plus the potential energy is lowest and it is equal to 0. Now at point C, the kinetic energy is equal to 0 because the pendulum will stop moving at point C and also point B, but it is at a height h above the point A. So the potential energy at point B and C is equal to mgh. So what I can basically say is half m Va square is equal to mgh. This is conservation of mechanical energy for a pendulum, where the kinetic energy and potential energies interchange with each other, but the sum of the kinetic energy and potential energy remains conserved and constant. So for solving this problem, let's make a diagram first. So basically you have this pendulum which is of length 1 meter and it moves to a maximum angle of 60 degrees, correct? There is a maximum angle of 60 degrees. Now let's look at like this. It is asking me about the maximum speed. First figure out what is the point where we will have maximum speed. We will have maximum speed at the bottommost point. So at this point the speed of pendulum will be maximum. Let's say that speed is v. Okay. Now the second thing that I am going to do, I know that at the highest point, at this point, let's call it as b, the speed of the pendulum is going to be 0. Okay. What else I need? If I know this height h, using this height h, I can use conservation of mechanical energy and I can easily find out v. So for finding out this height h, what I need is trigonometry. Using trigonometry, you know that the length is 1 meter, correct? The length of string is 1 meter. So basically, let's look in this triangle, the red triangle. In the red triangle, this angle is 60 degree. This side is 1 meter. So if I want to find out this side, let's name it x. Okay, what I can write in this triangle, if this side is x and this is 1 meter, I can write that cos of 60 degrees is equal to base by hypotenuse. Base is x and hypotenuse is 1 meter, correct? So according to this, x is equal to 1 cos 60. That means 1 into cos 60, that is half, or x is equal to half meters, correct? So if x is half meters and this whole length is the length of pendulum which is 1 meter, then this h which is equal to 1 minus x will be equal to 1 minus 0.5 or simply 0.5 meters. Okay students, now we can apply conservation of mechanical energy to this problem. So according to conservation of mechanical energy at point B is equal to mechanical energy at point A. So at point B, the speed is 0. So the kinetic energy at point B is 0. Okay. This is Ke at B. Okay. Plus, now what is the potential energy at point B? The potential energy at point B is equal to mgh. Correct. This is Pe at B. Now for the mechanical energy at point A. At point A, the kinetic energy is equal to the maximum kinetic energy, which is equal to half mv square, correct? This is half mv square. This is kinetic energy at A plus, and the potential energy at A, which is equal to 0 because the height of point A is 0. So this is the potential energy at A. Okay. Now we can solve this equation, right? You know the value of h is half. So let's just put the values. Mass is 2 into g, which is, let's say the value is 10, into h. H has the value half meters. Half, okay, half is equal to half again mv square. M has a value of 2 into v square. We have to find out v, correct? So basically when I do this, what I get, v square is equal to 10, or when I solve this, I get root 10 meter per second. So the maximum velocity of this pendulum is equal to root 10 meter per second. Okay, students, in this problem, what we have done is we have used the conservation of mechanical energy. Now we will look at another problem. In this problem, a ball is thrown vertically downwards, directly downwards with a speed of 10 meter per second. Okay, the part A is we have to find out initial kinetic energy. For initial kinetic energy, you know that initial kinetic energy is equal to half mv square, correct? The kinetic energy is equal to half mv square. So for the initial kinetic energy, we'll have to take initial velocity or initial speed. So this is half m, that is the mass. The mass of the ball is 1, okay, into v. V is equal to the initial speed for the initial kinetic energy, and this is equal to 10, correct? So basically 10 square. So the initial kinetic energy on solving we get 50 joules. So the initial kinetic energy is equal to 50 joules. Correct, students? Now let's look at part B. Part B is asking for the change in potential energy after the ball has fallen 30 meters. See, the ball is going down, correct? So the ball is here and it is coming down. When it is coming down, the potential energy of the ball is going to decrease, correct? The potential energy is going to decrease because the ball is coming down. So the change in potential energy, let's name it delta PE. Delta means change, P potential energy. So it is change in potential energy is equal to minus mg h, correct? Where h is equal to 30 meters. We have taken minus sign because the potential energy is decreasing when the ball is coming down. Okay, so this is equal to minus, the mass is given as 1, g, let's take the value as 10, and the height that is being dropped is 30 meters. So when you solve this, you get minus 300 joules. So the change in potential energy of the ball when it has fallen down 30 meters is minus 300 joules. Now let's look at part C. In part C, we have to find out the speed of ball at instant B. For finding out the speed of ball at instant B, I need the kinetic energy of the ball at instant B. For doing that, I can use conservation of mechanical energy. Okay, so let's say that the kinetic energy at the instant B is equal to KB. So kinetic energy is equal to kb, correct? So let's use conservation of mechanical energy. According to conservation of mechanical energy, the mechanical energy at the initial position is equal to mechanical energy at the final position. Initial kinetic energy ki plus initial potential energy, that is ui, is equal to the final kinetic energy or the kinetic energy at b plus the potential energy at b, correct? So Ki, the initial kinetic energy is 50 joules, is equal to what we can do. This is Kb, the kinetic energy at B, plus Ub, that is final potential energy, minus Ui, that is initial potential energy. Now this is final potential energy minus initial potential energy, correct? So this is basically change in potential energy. So from here, what I can write is that 50 is equal to Kb minus 300, correct? Kb minus 300. So when you do this, you get Kb is equal to 300 plus 50 is equal to 350 joules. Okay, so basically the kinetic energy at the instant in part B is equal to 350 joules. Now for the speed, I know the formula for kinetic energy is half mv square is equal to 350. So solve the problem here in this part. Okay, in this small part we'll solve the problem. So half the mass of the ball is 1 into v square is equal to 350 joules, correct? So when I solve this, I get v square is equal to 700, or V is equal to root of 700 meter per second. So the speed of ball at the instant in part B is equal to under root 700 meter per second. Thank you students. That is all for this lecture. All the best.